Okay, so what we have seen so far is that changes in the quantum numbers of an atom are called spectroscopic transitions. This is where an atom goes to an excited state when it absorbs a photon. Remember, a photon is this fundamental pseudo-particle of light. So we can draw this as atom A plus h nu going to an excited state atom A. That's A with the little Tinkerbell sign. So this is the basis of all spectroscopy, looking at what happens when atoms absorb and emit photons. Now, as we've seen, because of the wave functions and the dipole operators, we have selection rules that must be followed. For example, we've seen with atoms that you have allowed changes in the angular momentum quantum number L as plus or minus 1, and you also have a selection rule for the projection of the angular momentum, orbital angular momentum, delta m sub L, and that must be 0 or plus or minus 1. So for example, if you start out with helium, which is a 1s2 configuration, and it absorbs a photon of the proper energy and promotes it to a 1s1 2p1, for the electron that went from the 1s orbital to the t2p orbital, the change in L would be equal to plus 1, and that's an allowed transition. However, if instead you were trying to get a transition from the 1s to a 3f orbital, that would not be allowed because the change in L would be equal to plus 3. So these are our selection rules for allowed transitions. Later on we'll see that you can have transitions that are forbidden, but for the time being we're going to set those aside. Again, we're using the orbital approximation. We're just checking to see how appropriate it is. So as I mentioned, these transitions are moderated by the transition dipole operator, which is mu with a little hat, and then the subscripts f and I. What the transition dipole operator does, it couples the initial and final states. So final state is F, initial state is I. So for example, we have A plus h nu going to A star. The initial state is in the ground state of A, it absorbs a photon, and the final state is an excited state. So that would be an absorption event, where the atom absorbs a photon, an electron is promoted from the ground state into an excited state. Alternatively, you can have the reverse process, where you have an excited atom, A star, that emits a photon h nu and returns the atom back to the ground state. Of course, it doesn't have to go back to the ground state. It can go back to any of the lower lying states, but just for the sake of illustration here, we have it going from an excited state initially, emitting a photon, and then winding up in the ground state, and that would be emission. No matter what the initial and final states are, we always draw the operator the same way, because what we're curious about is the value or the magnitude of the transition dipole, which is simply mu sub Fi. Now in general, the greater the magnitude of mu Fi is, the more likely the transition is, or the more intense transition. So you can think about going back to Beer's law, where you have that the absorption is equal to epsilon times B times C, where C is the concentration of the absorbers or emitters, B is the path length, and E is this molar absorptivity. You can imagine that the molar absorptivity probably has something to do with this transition dipole. And when you draw this out quantum mechanically, we see that this is the integral of the dipole operator operating on the initial wave function, the initial state wave function, and then the wave function for the final state, of course the complex conjugate of that, multiplied by that result, and then integrating it over all space. If this is equal to 0, that would be a forbidden transition. If this is not equal to 0, then it would be an allowed transition. And again, the greater the magnitude of the transition dipole, the more likely the transition and the more intense it will be. Okay, we'll discuss more of this in a little bit, but we saw that the Hund's rules tells us that atoms prefer to maximize the multiplicity. The multiplicity is equal to 2 times the absolute value of the spin quantum number plus 1. Then, of course, the spin quantum number is simply the sum of the component spins. So we have all of our electrons, sum all the spins up in that orbital, and that'll give you the value of the s quantum number, and then the multiplicity is 2 times that plus 1. Now, as we saw, because each electron has a spin of either value of either plus or minus 1/2, if we have 2 electrons, if they're paired, the spins cancel and we get a spin quantum number of 0, and then that would mean that the multiplicity would be equal to 1. If the spins are aligned, then we see that the values add together, and again we're taking the absolute values, so if they're both negative or both positive, it's inconsequential. The spin quantum number would be equal to 1, and then of course the multiplicity would be equal to 3. And we saw the paired electrons give us a singlet, and the aligned electrons give us a triplet. So the things that, going back to Gen Chem again, the Aufbau principle, that tells us how electrons fill as you're going from atom to atom. So you can predict what you think the electron configurations would be. Hund's rule, on the other hand, is really more for dealing with excited state situations, or atoms that are not in the ground state. So for example, our 1s2 helium atom, it absorbs a photon. It can go to another, if there is an allowed transition. The question is whether or not the spin is changing or not. So going from a 1s electron to, say, a 6p, is the spin going to remain paired, or is it going to flip and they're both going to be aligned? Now, let's not get ahead of ourselves too much, but for the time being, let's just remember what the rule is for an allowed transition, is that spin is not allowed to change. So no matter what the case may be, the spin may not flip, and you're always going to wind up with the paired electrons, the spin pairing. But again, let's set this aside. Just remember, for a transition, spin is not allowed to change, and we always get singlet to singlet transitions and triplet to triplet transitions. But as we mentioned earlier, when you go from paired electrons to unpaired electrons, situation's a little murkier because, well, it's singlet in the ground state because they're paired, but you could have singlet aligned states in the upper lying state. But don't worry about that. That's not important right now. Just remember, spin may not change during a spectroscopic transition. You stick with that, you won't have any problems. So repeat after me. Spin may not change during a transition. All right, thanks. Okay, that brings us to our next thing. So let's think about what else is happening with electrons and atoms. Now, remember, we can pretty much ignore what's going on with the nucleus because of the Born-Oppenheimer approximation. And again, due to the centrosymmetry of atoms, this is perfectly fine, and we just get the electrons and move along with the nucleus through space. And instead, we can just focus on what's going on with the electrons. All right, so let's remember some basics from electromagnetism. You'd think I could just re-record this, but what fun would that be? You got my flubbing all the rest of the semester. You're going to get it now, too. All right. Anyways, moving charges create magnetic fields. So we know this. We have a charge moving through a coil. It creates a magnetic field, and that's how you have power windows and all that good stuff. Now, spin has a projection. It has only 2 flavors, so we call it up and down, a lot like a magnet. Kind of see where this is going, don't you? Now, the orbital angular momentum also has a direction. Remember the projection? It can be either positive or minus. 0 means that that it's just laying perpendicular, whereas plus or minus tells you it's pointing variously up or down. Now, you can imagine that because you have the spin of the particle and the movement of the particle as it goes around, the spin and the orbit, they couple. These are both vector quantities, so they add together. You can test this yourself. Go get a bicycle wheel, spin it, and then try tilting it one way or the other. And you'll notice that there's a bias one way, and if you use the right-hand rule for the direction of spin, it'll be exactly the way that your thumb's pointing, right? So this is just basic physics. So let's take a closer look at this and what this has to do with atoms. Okay, so this is spin-orbit coupling. So let's take a look at where this comes from. So we have 2 things going on. We have an electron moving inside this orbital, and then the electron itself is spinning, and we're going to be looking at the coupling, or the interaction, between the angular momentum and the spin. So we have the orbital angular momentum, which is quantum number L. Shown here, it's spinning that away. It means that it has the projection upwards. Now the electron is moving about this orbital and it has its own spin, and it's spinning the same direction as depicted, and then the spin is pointing up. So these are both vector quantities, and we're going to add these two vector quantities to get the resultant, which will be the total angular momentum. And as we can see, these add together, and then we have a total angular momentum, which is a new quantum number, J. And that's going to be greater in magnitude than either L or S. And this is the total angular momentum of the electron in this orbital. Okay, now of course we know that electron can have, well, you expect electrons to have both spins. One electron will have one, the other one will have the other. So if we have the case where the electron spin is going the other direction, and therefore that means that it's downwards, then the projection will be subtracting from L, and J will be attenuated, and it'll go down a little bit. So we see that we have two possibilities for J, each differing by a factor of 1, because the projection is either 1/2 up or 1/2 down. And remember, with the spin quantum number, it's always 1/2, and it's this vertical projection because you're looking at its projection in the same direction as L. It can only be plus or minus 1/2. Okay, so this new quantum number J takes this into account. Sounds pretty good, doesn't it? Okay, so here's where it gets fun. We have to see how to keep track of this, and that's where we have these atomic term symbols. Now, what all I really want you to know is to be able to look at a term symbol and know what the things are, worry less about where they come from, but we'll go through it anyways. So the term symbol is in green, in black, you have a big number X with a superscript in green, which is the multiplicity, and a subscript in red, which is the total angular momentum, of M, L, and J, as shown. Capital L is the total angular momentum that we just discussed, and it'll have orientation capital ML. So now we have another new quantum number for an atom. Capital S is its total spin quantum number with projection capital M sub S. Capital J is the total angular momentum, which also has a projection M sub J. And these are all our new quantum numbers. And these describe the atom. So finally, L. Where do we get this? Well, we use these Clebsch-Gordan series. So let's look at where these come from. Okay, so the Clebsch-Gordan series, we'll use this a few times, and it's pretty straightforward. But remember, this is telling us all the possibilities. So L can be L1 plus L2, L1 plus L2 minus 1, so on and so forth, until we get to the absolute value L1 minus L2. Now, as you can see here, we have L1 equals 2 and L2 equals 1, and we're looking at the three different projections, plus 1, 0, and minus 1. And we can see that L, the total orbital angular momentum quantum number, will be equal either 3, 2, or 1, depending on the orientation of L2 with respect to L1. And that's what the Clebsch-Gordan series is giving us. It's giving us all the possibilities. So it isn't that this is what an orbital will have all three of these necessarily. It's that, well, an electron with this projection or an atom with this electron can have any of these. These are all the possibilities. This isn't necessarily describing a single atom. That's why I don't want you to worry too much about this. And again, focus on being able to look at a term symbol and decipher it. Okay, so as you can see, capital L is always going to be greater than or equal to 0, always. And it turns out that the term symbol, that letter X, is indexed just like orbitals are. So 0, 1, 2, 3, 4 for capital L, X will be capital S, P, D, F, G, and H, so on and so forth. So a P2 configuration can give you three possibilities, where L1 minus L2 is 0, that's S. L1 plus L2 is 1, that's P, and L1 plus L2 is 2, that's D. Three different possibilities for the term symbol for two electrons in p orbitals, and we indicate these by these capital letters. Okay, so what is multiplicity? Well, again, we use the Clebsch-Gordan series, where we have capital S will be all the possibilities of adding the two spin quantum numbers together, S1 plus S2, S1 plus S2 minus 1, so on and so forth until you get to the absolute value of S1 minus S2. Little s is always going to be 1/2, so with 2 electrons you only have 2 possibilities. Capital S will be either equal to 1 where they're going the same direction, or 0 where they're paired up and go in opposite directions. So we only have the 2 possibilities when you only have 2 electrons. With 3 electrons, you still only have 2 possibilities, and you can think about this a little bit. When they're either all aligned the same direction, in which case you get a spin of 3 halves, or 2 of them are paired and one of them's going another direction, and that's where they're going to be equal to 1/2. Because again, you're always looking at the absolute values here. So you can look at this yourself, how you get these different spin quantum numbers. Remember, you're just always adding the spin. So the multiplicity is going to be equal to 2 times s plus 1. And we saw this already with the singlet and triplet states. They're all paired, s is going to be equal to 0, the multiplicity is 1. If they're unpaired, s is not equal to 0, and the multiplicity will be different. And depending on the configuration, it can either be a singlet or a triplet. So you can start thinking about these as the number of possible ways to arrange it. With a singlet, there's only one way to do it, whereas a triplet, there's 3. So let's look at an example of this. So let's look at our good friend helium with this 1s2 configuration. Now, because all the electrons are in s orbitals, we know big L is going to be equal to 0 because there is no orbital angular momentum. And because the spins are paired, the spin quantum number is going to be 0, and therefore the multiplicity is going to be 1. So, because we know that this is a singlet, this will be a 1s configuration. Looking at the excited state, we have 1 electron promoted to a p orbital. Now we have L equals to 1 because of the p orbital. So big L is going to be equal to 1. And the multiplicity is either going to be 3 or 1, depending if the spins are aligned or if they're paired up. So for this excited state helium atom, we can have 2 possible states, a 1p or a 3p. Both of them are possible. Ground state helium is always going to be a 1s state. It's the only way to do it. But when you excite one of those 1s electrons into a p orbital, then you can get either singlet p or triplet p, depending on what happens to the spin of the electron during the transition. Okay, so one thing we haven't mentioned too much about, we haven't done that subscript, that other quantum number, J, the total angular momentum. Well, with 1 electron, the orbital angular momentum, you simply add the orbital angular momentum plus the orientation of spin. Straightforward. But with multiple electrons, well, let's look at that next. So with closed shell, it's simple. Big J is always going to be equal to 0 because all the spins are paired and all the orbitals are occupied. All the different orientations of the orbital are occupied. Otherwise, you have to use, again, the Clebsch-Gordan series. And that's where big J is going to be big L plus big S big S minus 1, so on and so forth, until you have the absolute value of big L minus S, and J is always going to be greater than or equal to 0. So let's just look at some examples here. So first, calcium. That's neon with a 3s2. L is going to be 0, S is equal to 0, so you only have J equals 0. The spins are paired, there's no orbital angular momentum. This will be a singlet S state. That's what ground state calcium looks like. So let's promote one of these electrons into a p orbital. So now L is equal to 1, and spins are either paired or unpaired. And just like we saw with helium, we have 2 possibilities. We either have 3p or singlet p. Well, let's look at all the different possibilities for J. So J, as you're adding L plus S, L is always going to be equal to 1 for excited state calcium, but S can either be equal to 0 or 1. So if L is equal to 1, then we have either adding 1 or adding 0, so J could be equal to 1 or 2. In the other configuration, or the other term that you get from subtracting 1 from there, you either get 0 or 1. So we have 3 possible values of J, 0, 1, and 2. And we have 2 possibilities for the multiplicity. So you can see we have 5 different combinations of 5 different combinations for this 1 electronic configuration. Triplet P2, triplet P1, singlet P1, triplet P0, and singlet P0. This is why let's not worry about how to assemble term symbols, but let's focus on how to interpret them. All right, so let's look at one more. We all love oxygen, right? We know oxygen has this is paramagnetic, 2s2, 2p4 in the ground state. So because no matter what we have here is that you have two possibilities. Because one of the orbitals, one of the p orbitals is paired, it depends if it's a projection of plus or minus 1 that's paired or the projection 0 that's paired, and we can get different values for L. If L is equal to 0, that would be when the paired electrons are in 0, and therefore the plus or minus 1 cancel out. And then S is equal to 0, because again the spins are now paired up, and we get singlet S. If L is equal to 1, that means then the spins are either paired or not, and you have two possibilities, singlet D or triplet P. So, as you can see, there's a lot of possibilities. The goal is to read and understand term symbols, not to develop them from scratch. I want you to be able to look at them and know what they say, but not necessarily sit there and agonize over every single possibility. Sound like fun? Deal.